Algebra 2, 5.04. Just a quick note that you might be looking for 5.03. Check which homework assignment was assigned to you on the last day you were in school. So just a hint there. We're going to be comparing the properties of two functions, each represented in a different way. So we know a bunch of functions so far. The ones we've just learned are exponential functions, and we're going to compare those to some of the functions that we've been working on previously. Before we do that, let's make sure that we remember how to graph and create exponential functions. The example that we saw in class, so if you were able to finish this up on your own, no need to watch this, you can skip it, or maybe you want to watch it for a quick refresher. So what we're remembering is that we are trying to find the function, the exponential function, ab to the x, and we need to find the values of a and b for our function. And all we have is we have the graph of the function with a couple of points, and we want to use those points to help us solve for the values of a and b. So as we've seen in the past, we kind of have a process that we go through. We will first solve for a. So we can use one of these points, it's an x and a y value, and plug it into our function and use that to solve for a. Then we can use the value we find for a and solve for b. So I've started us out. We're going to choose the first point. It doesn't matter which one we use. We'll plug it in. So when x is -1, I have a times b to the -1, and that's going to equal 3. And what I'm trying to do is solve for a. So I've written in green here. I'm going to multiply by b on both sides because b to the -1 times b to the +1 is b to the 0. And b to the 0 is 1. So I have a alone on the left, and on the right side I have 3 times b. So here I've solved for a. It's not a number that we know. It depends on b, but it's going to allow us to move onward and use this new value of a to solve for b. So just like we've done in the past, we're going to use the next point with our value, our new value for a, to solve for b. So we have f of 3 is, now our function is of the form a b to the x, and we're going to use what we found for a, which is 3b here. So it's going to be 3b times b to the x. It's not the x, it's our x value is 3. B to the 3 equals 16/27. Okay? So we're solving for b. b times b to the 3rd is going to be b to the 4th. So I have 3b to the 4th is equal to 16/27. Now I need to multiply by 1/3 on both sides. And this is going to allow me to cancel the 3's here. And now I'll have b to the 4th is equal to 16/81. That's 27 times 3. And now I need to I need to find a way to get this to be b to the 1st power. So the way that I'm going to do that is I'm going to raise both sides to the 1/4 power. So on the left side now I have b to the 1st power because 4 times 1/4 is 1. And remember that when I have an exponent, when I take a fractional base, I can apply the exponent to both the numerator and denominator. And 1/4 is the same as taking the 4th root. So I have the 4th root of 16 over the 4th root of 81. And what will I multiply by itself 4 times to get 16? Will be 2. And multiplying itself 4 times to get 81 is 3. So the b value that I'm looking for is 2/3. And so my function is f of x is equal to, and I know the b value is 2/3. So 2/3 of the x. And the question is, what is the a value? Well, the a value is 3 times whatever the b value is. So real quickly, a is equal to 3 times 2/3, and 3 times 2/3 is just 2 because the 3's will cancel. So my a value is 2. And this should make sense because my exponential function is getting closer and closer to 0 as I move towards positive infinity, as x moves towards positive infinity, so I know that I should have a fractional base. All right, so what I want us to do is just think about some of the characteristics that exponential functions have. In one direction, they are going to have a great amount of change, right? So for this function, it's changing a lot as I move towards the left. And as I move towards the right, it's starting to shallow out and get closer and closer to a value. Okay, and so that's one of the things that is going to be important as we move on and compare it to some other functions. So here I'm showing two different exponential functions and how one of them is going to increase rapidly and the other one is going to kind of shallow out. So 2 to the x is going to increase rapidly. So its rate of change is increasing as I move towards the right. So rate of change increases as I move towards the right. For this function, 1/2 to the x, this function, the rate of change is decreasing. It's getting shallower and shallower. Okay. So these are going to be some important characteristics. And of course, the opposite is true as I move towards the left. As I move towards the left, the rate of change here is increasing. It's getting steeper. And for 2 to the x, the rate of change is decreasing. It's getting shallower. So this is going to allow us to start answering some questions. So here's this question. The linear function f of x is graphed below. The function g is given by g of x, which is equal to 2 to the x. And there's a couple of questions. So which function has the larger y-intercept? This is a pretty easy question. Let's take a look at what our game plan could be for comparing g and f. And we'll just make sure we know this is f. What we want to do is we want to represent both of the functions in the same way. So that will really help us look at them side by side. And it's almost always going to be advantageous to graph both of the functions. So since I have f already graphed, why don't we go ahead and graph g of x? So pause the video now, go ahead and graph g of x, and then try to answer both a and b on your own. And once you've given those a try, go ahead and press play and we'll discuss. So graphing g of x, it's 2 to the x, so when x is 0, the value of g to the x is going to be 1. When x is 1, the value is going to be at 2 to the 1. And it's going to be an exponential function, so we know that it's going to look like that, and as I move towards the left, it's going to approach 0. So the answer to A is pretty obvious. The y-intercept of g of x is only 1, while the y-intercept of f of x is 5. So f of x has the larger y-intercept. For B, which function has a greater average rate of change between 1 and 5? So between the x values of 1 and 5. Let's just say 5 is over here somewhere. Well, how can I tell which function is changing more? Which one has a faster rate of change? The average rate of change, just like the slope, it's the steepness, right? How much is something changing? Well, the steeper it is, the more it's going to be changing, right? So which of these functions is steeper? It's pretty obvious that g of x is much steeper than f of x is. And the way that we could do this is we could actually compute the average rate of change between the values at x equal 1 and the values when x equals 5. We don't have to, but we can do it to prove it to ourselves that g of x has a greater average rate of change than f of x. So why don't you go ahead and pause the video, try computing the average rate of change. Remember, it's where you finish minus where you start, divided by the number of spaces it took you to get there, and see which one is bigger. And just to help you out, the function f of x is a linear function, and you can find what the slope of that linear function is if you need to. All right, so let's find the average rate of change for g of x first. So the average rate of change between 1 and 5 is going to be the point I'm at when x is 5. So that's going to be g of 5, where I finish, minus where I started, which is when x is 1, divided by the number of spaces that it took me, which is from 1 to 5, which is 4 spaces. When I plug in 5, 2 to the 5th power, and when I plug in 1, 2 to the 1st power, divided by 4. 2 to the 5th is 32, 2 to the 1st is 2, divided by 5 is going to be 30 divided by 5, which is 6. So the average rate of change for g is going to be 6 units. Okay, so every time I hop to the, on average, every time I move to the right one, I'm going to go up 6. Now let's take a look at the linear function. So the linear function has a slope, and we can tell what the slope is because when I move, it's a straight line, so the slope is always constant. So when I move to the right 1 unit, I'm going to go up 5 units. Right? We can create this little slope triangle right here, and we know that this is going to be the same slope for the entire straight line. So the average rate of change between 1 and 5 is going to be whatever that slope is. It's going to continue being 5. So the average rate of change for f is just going to be 5. Now we could of course use the function. Let's say that we were given the function and that f of x is in fact, and the slope is 5, so it's going to be 5x plus 5 because the y-intercept is 5. And so we could use the average rate of change formula in the same way that we did before. So we'll have f of 5 minus f of 1 divided by the number of spaces it took, which is 4. Well, using this formula, right, 5 times 5 plus 5 is going to be 30. And f of 1 is 5 times 1 plus 5, which is 10 over 4. This is 20 over 4, which is 5. And so we can see that the average rate of change for g is going to be greater. And we could tell because the exponential function appears to be steeper. Okay? And in general, this is a property that is going to show up over and over again. An exponential function is going to look a lot steeper than, say, a linear function. Okay? And it's going to only get steeper and steeper as we move onward. What we're going to see now is another comparison between two functions that we've seen already. So here we go. An exponential function of the form a times b to the x passes through these 2 points, -1, 3/2, and 1, 6. The function g of x is the square root function graphed below. So to give you a little practice, the first thing that you're going to want to do is find what the values of a and b are so that you can, really understand your function. And you might want to go ahead and graph your function f of x so that you can compare it to g, and then answer these 2 questions. How are the 2 functions different, and in what ways are the 2 functions similar? And what I'd like you to do is post your answer to how the 2 functions are different. So part B, I want you to post that in your comment. So your comment should have a question or an answer to someone's question and your answer to part B. Okay? And we'll discuss this in class.